chat and Q&A.
Yes,
and
I will do
raise
that in
your
the...
hand or whatever, trying to make it interactive.
And I have YouTube and QA and chat. I'll open here, so I should see if something pops up. Do you see my question in YouTube chat? Because for me it says something went wrong. So it's even possible to post questions there.
So I can't see your question on YouTube, but I see the chat. Let's see.
Because I tried to post something there, but it doesn't. It just says an error.
Ah, you know, you're right. I just wrote it there, and as well I got error.
Can you see mine?
No.
No?
So basically,
But Marco, yours is in the chat of Zoom, not the YouTube.
Okay. You're talking
I
about...
can see yours.
Okay.
so YouTube chat seems not to be working.
Okay, since it's 05, we can slowly start. I'm about to hit record, so once I hit record, I will tell you, Viliami, so whenever you feel ready, you can start introducing the speakers, okay?
Okay.
And we are ready to go.
Okay, welcome back to BrainHack Micro2Macro event. We are starting the second unconference of this meeting shortly. For that, we have two excellent speakers ready to provide details on machine learning and how it can be used to hack the brain. Chu Yang from School of Information and Electronics at Beijing Institute of Technology will be the first speaker, and Hao Chang from the University of Pennsylvania Perelman School of Medicine will be the second speaker. This session can be followed both in Zoom and YouTube, and you should be able to ask questions in both those platforms, but it seems that there's some issue with the YouTube comment field, so try to get to the Zoom to ask questions. If you want, you can also raise hand and we will give you option to speak out loud later after the speaks. And there should be plenty of time after the presentations for more questions. And now, without further ado, please welcome our first speaker, Chu Yang.
Thank you. I'm very happy to, I'm Chu Yang from Beijing Institute of Technology, and I'm happy to present our works on brain macrostructure imaging. Since brain macrostructure imaging is based on diffusion MRI, let me first give a very brief introduction to diffusion MRI. To understand how brain works, brain wiring is what you need. And neurotracing on non-human primates was the only option until diffusion MRI was developed to provide a non-invasive tool for imaging brain tissue organization. It is sensitive to water diffusion in tissue so that it allows us to infer tissue microstructure and establish brain connections. This presentation will focus on tissue microstructure or brain macrostructure imaging, which is formally defined as estimating and mapping histological features of tissue using non-invasive imaging techniques. Brain macrostructure imaging provides valuable biomarkers for brain studies. These histological features can include, say, axon density, fiber orientation, axon diameters, and etc. So one important question is, how can we reliably estimate tissue microstructure from diffusion MRI? And this is what we are going to discuss today. Here's an outline of today's presentation. I'll first introduce some conventional model-based methods of tissue microstructure estimation. Then we'll introduce learning-based methods as well as its uncertainty quantification. Finally, I will summarize briefly and discuss a few future works. So conventionally, suppose we have a tissue sample. We can apply different diffusion gradients to that sample and acquire different diffusion signals. These diffusion signals are also considered measurements in the so-called Q space. Then we can design a signal model that relates tissue microstructure to the actual signals. Then by model fitting, we are able to reconstruct tissue microstructure. Diffusion tensor is a very basic model which provides measures like fractional anisotropy and mean diffusivity, but they are known to lack specificity. So more advanced signals have been developed. In particular, the Naughty model is arguably the most widely used one in the studies of brain. It models water diffusion with 3 different compartments, the intracellular, extracellular, and the CSF compartments. So here we have the signal model. And for each signal contribution, we have a model that relates tissue microstructure with the signal contribution. I'm not going to the details of this model. So what we will have here is simply know that there are 3 tissue microstructures in the knowledge model, like the intracellular volume fraction, CSF volume fraction, and orientation dispersion. And they are all encoded in this signal model. So by model fitting, we are able to estimate these tissue microstructure measures from the observed diffusion signals. But this model is highly nonlinear and complicated, so it can be quite time consuming. To address this issue, Amico is developed to accelerate the estimation. It uses a linear approximation of the knowledge model with a dictionary-based sparse representation. So suppose this Y is the observed signal, we have a dictionary phi, and its dictionary coefficient F. In this phi, we discretized microstructure. And after estimating the coefficients F, you can use these coefficients to weight the predetermined discretized microstructure in the dictionary to get the final tissue microstructure estimation. However, these conventional model-based methods have some limitations, and researchers have developed learning-based methods. So let's first look at the limitations of these model-based approaches. In clinical settings, due to the constraint of the imaging time, it is generally achievable to acquire a reduced number of diffusion gradients, say about 30 to 60 diffusion gradients. But because of the highly complicated model, the estimation of tissue microstructure measures from this reduced number of diffusion gradients can be challenging. Another limitation or another challenge is that, again, due to the limited imaging time, the quality of the tissue microstructure estimation is limited by the low resolution of diffusion MRIs. So here we have an example showing 2 tissue microstructure reconstruction results. The left one is reconstructed from a high resolution DMR scan acquired with a large number, 270 diffusion gradients. And the right-hand side, the result is from a low resolution scan with only 60 diffusion gradients. We can already see visually the quality difference. So to address these issues, learning-based approaches have been developed. For example, Q-space deep learning, which was first proposed in this TMI paper, is developed to estimate tissue microstructure directly from diffusion signals. Since diffusion signals are also measurements in the Q-space, this method is referred to as Q-space deep learning. And also to address the problem of resolution, Q-space deep learning can be extended to super-resolved Q-space deep learning, meaning we are also increasing the resolution in the result. Although we can use some generic networks like multiple layer perceptron or generic super resolution CNNs, motivated by the Amico framework, where it shows that the sparsity of diffusion signals can be beneficial to tissue microstructure estimation. We also want to be able to incorporate such signal sparsity in the network design. Before we see how we design that, let's first look at this sparse reconstruction problem, where again we have this dictionary and we want to estimate F with a sparse constraint. Conventionally, this problem can be solved iteratively. For example, in the iterative hard thresholding method, we iteratively update the estimate of F, the sparse coefficient, in this way, based on the observed signal as well as the previous estimate. And here, W and S are matrices determined by the dictionary. And here, H lambda is a thresholding function. If we unfold this iterative process, we are actually able to get a network structure. For example, this is an unfolded process where we have 8 iterations. For example, this is the estimate of f at the first iteration. Then we multiply this f with a matrix S and add the result with w times y. Then we pass the sum to another thresholding function to get a new update of the sparse coefficient. But here, instead of using W and S determined by the dictionary, we are actually allowing the network to learn these weights. This has been shown to allow better reconstruction result and faster convergence for sparse reconstruction. So we're going to integrate this idea into our network design. So now let's look at how we formulate this problem. We use a 3D patch-based strategy where the input is a low-resolution patch of diffusion signals, okay, represented by these blue squares. The output is a high-resolution patch, high-resolution patches of tissue microstructure, indicated by these red squares. The input actually has a larger spatial extent than the output, so that we are able to use redundant information in the spatial domain for the resolution enhancement. And finally, the output patches are concatenated to get the final tissue microstructure map. And as we said, we want to incorporate the sparse representation of diffusion signals in the network. This network has 2 functional components. The first one does that computation of sparse reconstruction. And because now the input is a patch, instead of using this matrix multiplication, we are using 1 by 1 by 1 convolutions, which is equivalent. And this allows us to take patches as input. The second component just computes high resolution tissue microstructure from the low resolution sparse representation. And here we use a classic resolution enhancing architecture, a 3D ESPCN. So specifically, here's the network design. The first component corresponds to the unfolded process for computing sparse representation. And the sparse representation is then fed into the second component, which uses a number of convolutional layers to compute high resolution information. Here, note that in this ESPCN structure, the high resolution information is stacked in the channels, and they're rearranged to get the final actual high resolution information in the spatial domain. For example, if we have 1 low resolution voxel, which corresponds to 8 high resolution voxels, these 8 high resolution voxels will be stacked in the channels. We simply reorganize these outputs so that they correspond to a high resolution image in the output, final output. And this corresponds to this mathematical rearrangement listed here. To train this network, we just minimize the mean squared estimation error. This actually allows us to perform end-to-end estimation. So although we have 2 components, all the parameters, all the weights are learned jointly. This also means that we do not need to explicitly design the dictionary, because all these weights are learned from the supervision at the final output without needing a dictionary design. Before we present the evaluation of this method, let me also introduce the probabilistic version of that method, which not only allows uncertainty quantification for the result, but also improves the estimation accuracy. So uncertainty quantification characterizes the uncertainties of estimation results. In medical image analysis, it could inform downstream image analysis. For example, it can tell us which results are reliable, which we should proceed with caution. So intuitively, suppose we have this regression task. In ranges where we have a lot of data points, we are more confident about our fitted curve. But in ranges where the data points are sparse, we are less confident. So the result has more uncertainty. Also, the uncertainty can be categorized into aleatoric and epistemic uncertainty, where the first one refers to the intrinsic randomness of data, and the second is due to the lack of knowledge. Now, back to our network design. To allow uncertainty quantification or probabilistic super-resolved Q-space deep learning, we, instead of minimizing the mean squared error to train the network, we are now minimizing the negative log likelihood to train the network, which corresponds to this loss function. So here we are modeling the output with a Gaussian distribution, where mu is the mean and sigma is the standard deviation. These two are the outputs of the network. And by minimizing this negative log likelihood function, we are able to learn the network weights, which also allows us to, once we have the trained network, the network will also give us not only the estimate of the tissue microstructure, but also the variance, or in other words, the uncertainty of our estimate. And since we have now two outputs, the network structure is also slightly modified. We are now having two parallel paths in the second component, where the first one predicts the mean of the distribution, and second predicts the variance, in other words, the uncertainty. Additionally, in the deep ensemble strategy, we are using more than one models so that we can fuse the result of each model. They can be simply fused like this, where the tissue microstructure estimates is the average of each network output, and the standard the variance is fused slightly more complicatedly, but according to this definition. Also, since this is a hackathon event, here are some implementation details. We implemented our method using TensorFlow plus Keras for network implementation. We also used DiPy for some diffusion MRI pre-processing. Amico and the DiMaPy was used for tissue microstructure estimation. We also have some packages for image input-output and visualization. Also, if you are dealing with raw data instead of pre-processed publicly available data sets, there are also some useful tools that could be helpful. For example, the FSL BAT can be used for brain extraction, and FSL top-up and ADDI can be used for distortion and motion correction. To train the network, we need to acquire high-resolution diffusion MR scans, where the diffusion signals are acquired with a large number of diffusion gradients, as well as a high resolution. These high-quality scans can be used to compute the training tissue microstructure using conventional model-based methods. Or if you want to quantitatively evaluate your estimation result, these scans can be used to compute gold standard as well. Then using this high-quality tissue microstructure, we can train the network with the corresponding low-quality diffusion signals, which have a low resolution and a small number of diffusion gradients. So for evaluation, we use the HCP dataset, where the diffusion scans are of high quality. The resolution is very high, 1.25 millimeter, and it has 270 diffusion gradients. we subsampled these scans in the spatial domain and the Q space to create low quality diffusion scans that represent those diffusion scans in the clinical settings. And we want to see how well we can estimate tissue microstructure from these generated low quality diffusion scans. So here's the training process. We see after about 20 epochs, the validation loss becomes stable. Also, we use the validation loss to select the hyperparameters like the channels at each layer. So here are some evaluation results. First, here's a qualitative example. We see either the deterministic version or the probabilistic version gave results that resembles the gold standard. Also, we compared these methods with ESPCN directly, meaning we use ESPCN to map diffusion signals directly to tissue microstructure without using signal sparsity. And qualitatively, we see the error maps here of our method appear smaller than the competing method. And this is confirmed by the quantitative evaluation, where our methods have smaller estimation errors than the competing method. Here, we also considered other approaches like the conventional estimation method, amico plus interpolation. Also, we considered random forest regression and a few variants of the ESPCN structure. Also note that here we considered another version of a commonly used probabilistic strategy, the Monte Carlo dropout. And we observed that it actually increases the error of tissue microstructure in our case. We also computed the PSNR and the structural similarity, where higher values indicate better estimation quality. So again, our method has higher PSNR and SSIM than the competing methods. We also look at the uncertainty quantification results. So here's a qualitative one. We have the error maps as well as the corresponding uncertainty maps. We see some very similar patterns of these two maps. And for example, in these zoomed regions, when the error is large, we also observe a larger uncertainty in the map. And quantitatively, we correlated the error with the uncertainty, and we have observed significant correlation. These experiments were also repeated for different settings. We have tested different numbers of diffusion gradients and different data sets. In all these cases, the improvement is significant and the effect size is large in most cases. Also, the correlation between uncertainty and error is always significant. To summarize, we have seen that learning-based tissue microstructure estimation shows promising results and outperforms conventional model-based approaches. We have also seen how to perform uncertainty quantification for tissue microstructure estimation. Future work could include application of these methods to the study of neurological disorders like Alzheimer's disease, MS, PD, etc. In terms of methodology, we are able to improve the method by incorporating multimodal information. For example, the T1 or T2 weighted images are almost always available in diffusion MR acquisitions, and they have high resolutions, which could be useful. Also, we could transfer knowledge from a publicly available dataset to a private dataset so that we only need a very few number of training scans to perform these learning-based methods. So skip this slide, and I'd like to finally thank my funding agencies, and here's my contact info. I'll also be happy to answer questions after the second speaker. Thank you.
Okay, thank you. That was very inspiring, I think. I don't see any raised hands or questions from attendees. So if someone has something in mind, please raise your hand or write to the Zoom chat or questions and answers. In the meanwhile, I have one question for you. So do you see any clinical applications for the method in near future? If so, what kind of applications?
Thank you for the question. We are actually acquiring data for clinical applications. We are acquiring data for several types of neurological disorders. And we want to see if we are able to replicate the findings using high quality diffusion scans with low quality diffusion scans using our learning-based methods. So I think we should be able to finish that study within this year.
Okay, this sounds really promising. And one thing that I'm always wondering is that what happens if somebody moves their head during the scan? Can you use that kind of data at all, or can you train the network to realize that there is motion artifacts going on?
Although I have not been working on that, I have seen papers first to identify those motions, and I think their method also performs motion correction. I think it's a MRM paper very recently. So yes, it is possible.
Yeah, because that's the typical problem with clinical data, that somebody moves their head.
Yeah,
and
right.
you,
Yes,
yeah.
exactly.
Yeah, okay. I still don't see any questions. So if somebody wants to ask something, perhaps after the second talk is time for that. So, okay, let's thank again Chu Yang and give the floor to Hao Cheng.
Awesome, thank you. Let me share my screen. Can you guys see my screen?
Yeah.
Great. Thank you. Hello, everyone. It's great to be here virtually together with you. I've had a chance to glance through some of the projects of the hackathon, and it looks super interesting to me, which I had the time to participate. So I'm coming from University of Pennsylvania. I'm part of the member of the Pensive Imaging Center nested within the Department of Biostatistics, Epidemiology, and informatics. So my talk, I'm gonna maybe switch gear a little bit and talk about sort of a series of statistical efforts and methodological development that was mostly done by folks in our group in the task of addressing sort of site differences and batch effects correction for neuroimaging studies. So as you have all maybe seen and been working with many of the large consortium cohort study for neuroimaging studies, such as the Alzheimer's Disease Neuroimaging Initiative, UK Biobank study, and ABCD study, PNC, these are, in the past few years, the emergent efforts where a lot of the investigators are interested in putting together multiple sites of neuroimaging cohorts together using a multimodal imaging acquisition to help us to enhance the power and increase the sample size and integrate combining imaging markers to understand the underlying disease pathology. What's very interesting and important in order to be able to do such mega-analysis is that we urgently need a reproducible and scalable methods that are able to generalize our findings to other clinical studies as well. So one of the issues that we might be encountered in such mega type of analysis is various type of data variability that is observed in the imaging data. So naturally, data variability came from multiple sources. There are sort of biological variability, for example, due to social demographics and disease labels, clinical characteristics. Those are of clinical interest that we are hoping to identify. However, there's also emergent evidence of many unwanted technical variability. As mentioned in the previous talk, there could be motion, there could be differences due to scanner manufacturers, acquisition parameters. The variability could also happen in the downstream analysis when we are coding and pre-processing the imaging data from different ways. So here I'm just showing a few examples that have been reported, showing, for example, in the multiple sclerosis lesion volume characterization or segmentation, there's been reported substantial differences from even the same subjects that are imaged on different image scanners multiple times. The variance of such data differences between different scanners also shows some kind of spatial patterns and dependency that differ from one location of the brain from the other. And lastly, this example examine sort of the generalizability and reproducibility when we train a machine learning and prediction model from one part of a few sites of the data and try to generalize them onto another site. And in the presence of the scanner differences, we can see that it actually hurts the performance of the prediction in other studies. So this means that we need to address the questions and remove the unwanted technical variabilities that could happen in many stages of imaging acquisition and analysis. From the efforts that I'm also partly involved in is looking at more standardized acquisition pipelines and trying to quantify using traveling subject studies, quantify what the amount of the variability are from one scanner to another with the same study subjects that was scanned multiple times. There's ways to sort of handle the unwanted variability by removing them afterwards, after we have processed the data and acquired the data. And in the recent years, there's many efforts and large development in developing robust machine learning algorithms, such as using transfer learning that are invariant and robust to differences between sites and can borrow information from each other. So for this talk, I'm going to focus mostly in this middle process where we are trying to use statistical modeling to remove unwanted variability from the processed data and then feed into the downstream analysis. So the main methods that we are going to use and actually develop in many new directions are the combat methods. So a couple of years ago, it was first adopted by a former postdoc of our group, Jean-Philippe Fortin, and my colleague, Taki Shinohara. So this was the method that was originally proposed in the genomics literature. And when JP looked into a sort of age-matched data set from two study of DTI measure and looking into the fractional anisotropy and mean diffusivity maps, what he found is when you look at the voxel-wise comparison in terms of intensity of the FA values and plotting them using the blend ultimate or MA map, which shows the voxel-wise average intensity versus the voxel-wise difference intensity, you can clearly see a sort of systematic differences between one site to another site, in the sense that one site tends to have always higher value than the other. Also, such kind of differences depend on the location of the voxel in the brain. So some of the existing previous normalization technique after applied onto such data still shows such differences that was not completely removed. While using the comeback methods after the correction, we could see that the difference between the two sites are mostly diminished, regardless of the underlying actual intensity of the FA value within the brain. And that's what we want to see, right? And also, he has conducted a experiment by looking into the age association with respect to the FA value. And one of the results is showing that looking at the voxel-specific T statistic with the univariate age association, you can see that with respect to voxels that showing high signals, the ones after combined harmonization is actually having larger magnitude of the T statistics or effect size. While for voxels that don't show effects, it actually preserves the type 1 error and doesn't increase the T statistics. You can also plot the voxel-specific site differences in both mean and both variance, and indicating their spatial pattern of site differences in CSF and white matter structures. So what is the combat methods? Combat stands for combating batch effects, and it was the original method that was proposed by Ivan Johnson in the genomics literature. Essentially, it's a regression-based technique trying to model the difference by sites due to in the mean and in the variance. So it's similar to accounting for site as a covariate, but more than that. The model itself, supposedly we are modeling a imaging volumetric data from a certain RIV, from data subjects J and from site or scanner I. We essentially model this whole observation into two parts. One is the clinically interesting parts with the clinical covariates that can explain the data variability. But in addition, in the noise parts, we have two parameters, gamma and delta, gamma representing the differences in the mean value of such data due to the site differences. And the delta also accounts for the scale differences in the data. So it allows for voxel-specific or region-specific site difference modeling, but it also allows for kind of borrow information across different regions by imposing this Bayesian prior parameters, assuming that the site differences across different regions are all coming from similar distributions. And using the empirical Bayesian framework, we were able to derive a closed form solution for the posterior estimates of those site differences parameters. And then the step 3 is simply just removing the estimated site differences in mean and variance from the original data. And this is our corrected harmonized intensity values that we could feed into the downstream analysis. So as the methods has outlined, it has a several advantage of using such a approach in the sense that it preserves the wanted biological variability and trying to remove the unwanted technical variance. It's robust for relatively small sample size because it has this borrow information framework, allow you to estimate the site differences parameters from the across subspatial domain and borrow information from different regions. So since then, actually combat methods has been pretty successfully applied to not just the DTI data, but many other modalities. This is an example in cortical thickness measures. This has been also applied to correct for site differences in the resting state fMRI data from the ABCD studies, as well as in the task-based fMRI data in the same ABCD cohorts. So I have been very lucky to be involved in this large imaging consortium that was led by Dr. Christos Davasikos from Department of Radiology at Penn. And in particular, this iStaging consortium aims to bring together the structure, functional, and amyloid scan data from over 32,000 individuals from multiple imaging scanners. A couple of them are very familiar names, such as ADNI, BOSA, PNC, UK Biobank. And essentially, the idea is to incorporate all these imaging studies across lifespan and help us to understand the multidimensional brain development and aging process, and understand the local sort of subtypes and heterogeneous in the aging process. But one of the challenges, as you see and outlined in this age distribution, as well as the data distribution by age by different sites, is that we have so many different sites that don't have existing sort of overlapping or matched age samples. And they also are across wide span of the age range, that where the brain could potentially have a nonlinear kind of development trajectories. So definitely harmonized data across that many sites is one of the first tasks that need to be done in the iStaging Consortium. So with that, I have worked with a formal data analyst, the Raymond Pomponia, and the Crystal's group in trying to harmonize the data from that over 18 sites. That was the initial sample size we have, over 10,000 large MRI data across the lifespan. And the data that the measure that we've been focusing on is about 140 ROI region volumetrics data that was obtained from a hierarchical brain partition of cortical and deep subcortical structures. So we have extended the original combat framework into a more sort of adapt to nonlinear age trajectory over lifespan, and with a similar sort of framework to remove the site differences across data, across different studies, but in the same time accounting for the nonlinear trend in the volumetric differences. And here I'm just showing a few examples of before-after combat GAN harmonization. And you can see that the scale as well as the mean have been aligned onto a similar line after harmonization. And one of the advantage, as we illustrated in the paper, is also that the combat GAN after the harmonization, it shows the sort of advantage of not just to harmonize the data, but also help with a brain age prediction task that we are interested in the downstream. Through the simulation experiments that the Ray has conducted and using leave one side out experiments, we have seen that using the harmonized data of our nonlinear combat harmonization, we were able to achieve a much smaller mean absolute error in predicting brain age as compared to the unharmonized data versus the linear version of the combat methods. A product coming from this procedure is we have developed a Shiny-based web portal that help you to visualize the age trend that was obtained from our large iStaging Consortium data. And you can also upload your own data set to our web portal and harmonize your data with respect to this larger reference data that was made available through the iStaging Consortium. So here, a few examples of the age trajectory. As you could see, some of the sort of deep gray matter and total gray matter volume, we are seeing a decline even after puberty at age 20 or so, while for hippocampus volume, we see a faster decline after the age of 60, something like that. And it has been consistent with what's being reported in the literature in the past. We have used the harmonized imaging data for our next analysis, is trying to visualize these multidimensional relationship between the brain signature for agents such as brain atrophy, white matter hyperintensity, as well as the cognition and trying to display this, what we call the brain agent chart, to unveil the relationship between this model, multimodal metrics that coming from our data. And I'm not going too much detail for this paper, but I will defer you to this literature as recently being published here. So the second efforts that I want to mention is the work that we are interested in, not only just these potential site differences in the mean and the variance of the marginal observation for each volume or for each voxels. As we can see that the imaging data themselves are highly correlated spatially. So one of the questions that we were asking is whether there is evidence of scanner or site differences in the covariance structure across different regions and volumes. And indeed, this is what we have seen and observed from one of the studies that we are working with, which is the ADNI studies. So in particularly, we look at the 62 cortical thickness regions that was processed using the ANTS longitudinal pipeline from the ADNI data. And across about 500 participants that were acquired around 64 scanners that was manufactured by Siemens, Philips, and GE scanners, we have seen just visually some kind of differential patterns from scanners coming from, for example, GE scanners versus the Siemens scanners in terms of their covariance structures. So with that in mind, my colleague Taki Shinohara and our joint PhD student Andrew Chen was trying to coming up with a new methods that handle the site correction or scanner correction in the covariance structure. So just remind you that the previous combat methods is trying to model the site differences in the mean and the variance. Here we are extending this method and trying to incorporate measures across all the regions and voxels and model the scanner differences in this joint covariance structure of the data. So here we proposed what called the COVAT methods as opposed to COMBAC, which is correcting for the covariance batch effects in the data. And the model is quite straightforward in the sense that it's basically two-step approach where we first remove the mean and variance differences through the original COMBAC. And after residualizing such data, we then using a principal component-based decomposition and trying to use a second sort of process of comeback removal and trying to remove the site differences in the principal component scores, and then reconstruct our data in the callback corrected intensity values. So one of the direct products as displayed here is by visualizing the covariance structure before and after callback correction, we can see a much more homogeneous and consistent covariance patterns in the callback corrected data. And we also conducted experiments in trying to evaluate how does that kind of site differences influencing our downstream analysis of trying to predict biological phenotypes such as AD, Alzheimer's disease label, and sex, and how does that tells us about differences between sites. So for this, we conduct a random forest machine learning algorithm by looking into the degree and accuracy of using the uncorrected versus corrected data in predicting the scanner differences in the first plot. So in the first plot, what we actually want is the data are not able to do the prediction, right? So we want a lower AUC, and this is indeed what's being observed, that the uncorrected, we can almost perfectly tell which data is coming from which scanner versus using the COVAT correction, and that it's almost similar to a chance. And the original COMBAC corrections still have a fairly large chance of telling which data is coming from which scanner. when it goes to the biological variability, then the callback is shown to be able to tell the which data is coming from, which subjects are having Alzheimer's disease and which subjects are coming from male versus female in a much better framework, a much better way. I'm going to skip most of the simulations, but essentially we try different scenarios or simulation studies. Some are actually in favor of combat, and in that case, we can do as well as combat. And in cases where we have confounding between the covariates and scanner differences, our methods can still doing a pretty good performance in terms of predicting biological phenotype and not being able to differentiate the site differences. There's also a work that I want to mention is a recent development to trying to extend the previous framework into longitudinal data. So as we all know that the data coming from longitudinal studies within the same subject, they are dependent to each other. So simply using cross-sectional methods to correct for site differences might not be sufficient in completely removing the site differences in the data. So Joanne, who is a postdoc in our group, and Kristen, and they have extended framework and developed methods called the longitudinal combat to completely remove the site differences and while accounting for within subject correlations. Ongoing directions, there are many more directions that can be focused on, and there's still a long way to go in terms of harmonization. Some of the exciting directions that we are trying to work on, and you probably will see some of the work coming up in the next few months, is one thing is we want to develop a distributed version implementation of the combat and callback methods, in the sense that in the case of data are not able to share it across sites for the data privacy, how can we still exchange parameters and communicate between sites to conduct the harmonization process so that each site can have the comparable data to work with? We're working on extending the callback framework onto longitudinal data. And lastly, also, we are implementing our methods to apply to a correction in the functional MI data, and mostly for the functional connectivity data, and help improve the community detection in the downstream. So this, as I mentioned, there are a few joint efforts that's being developed for the harmonization using statistical methods. And here you can find a list of the software that's on GitHub that's available in both R, Python, and MATLAB. And I'm also very excited to be involved in two future sort of efforts and grant projects. One is the R01 grant by our group, mostly in methodological developments, trying to develop more advanced harmonization technique for multi-site and multimodal imaging data. And lastly, I was also one of the PEN co-investigator with this efforts led by a USC group by Dr. Paul Thompson, looking into the ultra scale machine learning algorithm to embed both genomics data and imaging data together to help us understand Alzheimer's disease. And with that, I'm going to conclude. And this is just a few folks from our group from before quarantine time, and not so serious, always have happy, fun time. I'm happy to answer any questions after the talk. Thank you for listening.
Okay, thank you, Hao-Chang. That was extremely interesting to hear, especially the part where you mentioned that maybe harmonization could be done without sharing data, because that's would be a big thing for clinical sites. I don't see any questions in the audience, unfortunately, so, and no raised hands. But I have just one question. I think we have time for that. Does the method require samples from matched clinical characteristics from different sites?
Sorry, can you say that again?
Sure. Does Does the method require samples from matched clinical characteristics from different sites?
Yes. That's a very good question. No, so that's actually one of the advantage of the combat methods is instead of requiring a matched sample where we are trying to control for the biological variability, combat accounts for biological variability. So you could, even if there might be not completely age overlap or for example, the gender distributions are different, we as long as we assume that the conditional distribution of our imaging data conditioning on those covariates remain the same between different sites, we can control for those as a covariate in the model instead of trying to match them, which is oftentimes hard to do. Well, the caveat is you can have a sample where you have complete non-overlapping clinical characteristics. Then that might not be a good scenario where we apply these methods. But in general, as long as we have some overlap in their distribution, then we can use the methods just as we use for the linear regression technique.
Okay, thanks. We have actually more questions. So Matteo has raised his hand.
Yeah, there are two very practical and simple questions. Thanks, Aoshango. It was a very interesting talk. So the first one is in terms of time consumption, how heavy are the combat family method? And the second question is in terms of number of subjects for each site. Are there some indications to know more or less how many subjects one should have in each of the different site scanners?
Yeah, thank you for the question, Matthew. For the first question, in terms of computational burden, actually, because the combat methods use what's called empirical Bayesian, so it's not fully Bayesian. It actually reduced computational cost by quite a bit. So it's very fast, actually. It doesn't require a lot of computational burden because we can come up with a closed form posterior estimation for the parameter. So there is a sort of a closed form solution. So it's not that much slower than just fitting a regression, so to speak. So mostly it depends on the dimensionality of the imaging data. And then for the second question, I don't have a rule of thumb saying like we should have at least that many, I guess, sample size for each site. But generally, when we are doing the estimation, like we have situations where we have about like 50 subjects per site. And actually the combat method, the advantage is it works actually better or works good compared to other methods in smaller sample size because it was able to borrow information across regions and voxels. But obviously, if you have too many covariates in your regression model, then we will need sort of relatively larger sample size to be able to fit those parameters.
Thanks.
Then there has been more questions in the audience as well. First one is this. Would it make sense to apply combat or covbat to harmonize one longitudinal dataset acquired with two different scanners? Each different scanner used to acquire data at each different time point.
Yeah, so it makes sense, but it's not ideal. So that's the thing that we are trying to develop in the future, because in longitudinal data, as I briefly mentioned, and I would defer you to that longitudinal combat paper, data acquired from the same subjects across different time points, they themselves are correlated because they're coming from the same subjects. So there is this dependency structure that we assume that there sort of scanner differences, the site parameters should also be correlated to each other. So using the cross-sectional combat or covbat disrespect such kind of correlation. And maybe I should go back to this result, where you can see using the cross-sectional convex correction, we still see evidence in their residues of uncorrected scanner differences. So the x-axis are different scanners, and this is the residualized, I think, cortical thickness volumes. So they're not completely removed, but using the longitudinal version, we are able to remove it in a better way. So definitely stay tuned for future method development.
Okay, thanks. We still have one raised hand in the audience, and I'm going to allow her to talk. So, Andreda?
Yeah, hi, sorry, I was typing the question. Very nice and interesting talk. So, yeah, my question is like, is it basically possible to apply the technique that you mentioned to your raw data and then get back like a harmonized one using like the software that you presented and the methods?
Yeah, I think so. I think so, as long as your, I'm assuming your data itself has, for example, multiple site and scanners in there. Then if you have a clearly defined site label or scanner labels, yeah, it should be directly applicable.
And then if you have data from just one site, then it's not, I mean, can you harmonize it against the database that you have, for example, from all the large
From
number?
yeah, so for the volumetric data, as I briefly talk about this website, so you need to have the same type of imaging. So here we were looking into the MI structure MI data, and specifically with respect to the volumetric data. So you need to have the same sort of spatial resolution or template of the RI. Once you have that, then you can upload your data and it will harmonize with respect to the larger data. But if, for example, if you have a voxel-wise image and this is the region sort of RI data, then it's not possible to harmonize with respect to using this tool. So you need to have a reference data that is on the same sort of spatial resolution and comparable.
Great, thank you very much for the clarification.
Yeah.
Now it seems that there is no more questions, so I would like to thank our both speakers today. And from my part, I just say happy hacking to everyone.
Thank you.
Thank you.
Thank you.
We will have now a 20-minute break, so feel free to relax until your time, 30 past your time. And then you can join the hacking space. This time you should be able to join the breakout rooms and to see the actual Bayesian room and not the coffee break room best as a Bayesian one.
So I will stop YouTube too.